Welcome back. In the second part of this lecture, we'll talk about finding the inverse of a function. So we're going to suppose that we have some function and we've already justified to ourselves that it's a one-to-one function. And so in other words, it must be passing the horizontal line test if we're thinking about the graph. And if we've got that, if we know that it's a one-to-one function and so therefore must have an inverse, then to find the inverse, we only need to do three things. First, rewrite our function instead of f of x equals, rewrite it as y equals, so that we've got x's and y's. The second thing that we'll need to do is exchange all of our x's with y's and all of our y's with x, which of course makes sense because that's what the inverse does. It's supposed to interchange our x and y values. And then finally, solve for y. And once you've solved for y, now you have your inverse function. And I'll put here as a little fourth part, which you could do if you had time, which is you can check your work. Because you know that if you found the correct inverse function, then f composed with f inverse should be equal to x, and f inverse composed with f should be equal to x. Again, that's not strictly mandatory for my class here. I'm not going to require you to always do that when you find the inverse. It's a good idea, though. If you have some spare time in a few minutes, it's always nice to check your work and justify that you're right. Okay, so let's find the inverse of this first function. F of x is equal to 3 times x minus 1 cubed minus 2. And so the first thing that we do is we write it as y equals. Next, I'll switch the x's and the y's. So instead of y equals, it's now x equals 3 times y minus 1 cubed minus 2. And now I just need to solve for y. So I'll bring the 2 over to the other side. I'll divide everyone by 3. I'll take the cube root. And then finally, I will bring that negative 1 to the other side. And there we go. So what I've done now that I've solved for y, that should be my inverse function. So f inverse should be cube root of x plus 2 over 3 plus 1. And again, you could check your work if you wanted to. You could go back and just double check that f composed with f inverse gives you x, and f inverse composed with f gives you x. All right, same thing with g of x. We never justified, by the way, that f was a one-to-one function, but that should be an easy one to justify. Because if you're thinking in terms of how do I know that this is a one-to-one function, you know it's a transformed cubic function, and you know that x cubed is something that is one-to-one. It definitely would pass the horizontal line test. But f is basically a cubic function that's been shifted to the right by 1, stretched vertically, shifted downward by 2. In other words, it's just a cubic function that's just been shuffled around a little bit. And so if it was one-to-one to begin with, if I move it left or right, up or down, stretch it, it'll still stay one-to-one. So that's my little justification on how I know that f of x is invertible. G of x is less obvious, and for that you would have to use your skills that you have in graphing rational functions. And if you did that, you would find that for this function, g of x, that it has a vertical asymptote and a horizontal asymptote, and looks a little something like this. It is, again, it's a one-to-one function. Any horizontal line would pass through your graph in at most one place. So because it's a one-to-one function, then we know that it should be invertible. And so therefore, we can find G inverse. And so let's do that. Let's first rewrite this as y equals. And then next we'll switch the x's and the y's, so that we'll have x equals y minus 1 over y plus 2. And now I'll solve for y by bringing that denominator up, expanding, and I'm going to now bring everybody with y's onto one side, and I'll bring everybody that doesn't have a y to the other side. So on the left side, I could factor out a y, and I could then divide. So y is equal to negative 1 minus 2x over x minus 1, which, if you wanted to, you could multiply top and bottom by negative 1 so that it looks a little bit nicer, as 1 plus 2x over 1 minus x. And so there we go. That should be G inverse. So I've mentioned this before, but it's good to bring it back again. This is one of the nice reasons why you might want to find the inverse of a function. And that's because, again, inverse functions exchange all of those x and y properties with the original function, and that includes domains and ranges. So if you happen to know the domain of f, then that means you know the range of f inverse, and vice versa. If you know the range of f, then you know the domain of f inverse. Now, if you're remembering from previous sections, finding the domain for a function was usually pretty easy. Finding the range was tougher because that required you to know what the graph would look like. So if we're thinking back to the example that we have here for g of x, this would be easy for us to find the domain. The domain is every x value except for negative 2. The range is less obvious what it is. What are the y values that we can get coming out of our function? And so the idea here is that if you wanted to know the range for g of x, you could still instead ask yourself about the domain of g inverse, because whatever the domain of g inverse, what are those x values? Well, that would be the range of g, the y values. And finding domains are always easy enough to do. So for example, for g, you could look at this and say the domain is everything except for 1. So for my range for g, it's everything except for 1. And that's one of the key ideas here, is that if we're looking at a function and its inverse, they're switching not just the points, but they're switching domains and ranges as well. So, for example, this function f of x, we want to find the domain and range of it. The domain is easy enough to find. We can say that this should be everything except for 2. Now, I don't know what the range is of f of x off the top of my head, and so I'd like to know what the range is, and I'll do that by finding the domain of f inverse instead. So first off, let's find f inverse. And this is, again, you can justify why this is a one-to-one function. You could think of this as the 1 over x function that's been shifted to the right by 2, stretched vertically by a factor of 5, shifted upwards by 3. If you started out as a one-to-one function and I've transformed it by shifting it around or stretching it, it'll stay as a one-to-one function. So I know that f should have an inverse, and so let's go find it. So my function is y equals 5 over x minus 2 plus 3. And I'll switch the x's and the y's so that x is equal to 5 over y minus 2 plus 3. And now I'm going to just work on solving for y. So what I've done so far, I started off by bringing the 3 to the other side, and then once I've done that, I took the denominator and brought it up so that I had x minus 3 times y minus 2. I divided by the x minus 3, and then nicely I will finish this off by bringing the minus 2 to the other side to give me y equals 5 over x minus 3 plus 2. And so this should be the function f inverse. Now, if we're looking at f inverse, this is easy enough for us to find the domain because, again, we're looking at what are the values of x that we can put in here, and it's pretty clear that any value of x except for 3 will be fine. So I'll say here that the domain for f inverse should be all the x values except for 3. And so that means that my range for f should be the same. It should be all the y values except for 3. Much like if we're thinking about the domain that we found for f, the domain was every x value except for 2. So that should mean for f inverse, the range is every y value except for 2. So there we go. We found for our function f of x, we found number 1, its domain was everybody except for 2. And then we found its range was every y value except for 3. And we used the domain of f inverse to find that.